diaphragme, alors ça fait des pixels à mort. Ou qui ferme le diaphragme. Ah, on l'a à l'envers cette fois-ci. La fois passée, j'ai réussi à l'avoir à l'endroit. Et ici, on l'a à l'envers.
C'est moins facile pour lire. Ça demande un petit effort de concentration.
Attends, comment j'ai réussi à faire? Parce que j'ai... Mais j'ai le même problème quand tu mets un fond derrière toi. Tu as un effet miroir et donc tu dois réinverser quelque chose dans la caméra.
Tu dois te mettre dos.
Ah oui, on le voit dans le...
Ouais, moi je laisse comme ça. Ainsi tu te vois si tu te balades. Mais même là, je le vois à l'envers.
Oui, c'est logique, si tu le vois là-bas.
Et l'autre là-bas.
Là-bas, tu le vois à l'endroit, il est dans le miroir.
Bon, il y a un effet miroir. J'ai dû corriger ça la dernière fois, mais je ne sais plus où. Activer. Afficher les affaires. Non, afficher les détails de la réunion. Afficher les paramètres du périphérique. Afficher les paramètres du périphérique. Haut-parleur, on s'en fout. Caméra H-Time intégrée. Activer les sous-titres. Bon, on peut mettre des sous-titres si tu veux. Passer en mode plein écran. Non, je ne vois pas. Comme ça. Mais je sais qu'on a dû le changer une fois. La fois passée, on n'a pas eu ça. Oui, mais non, on le voyait bien. Quelle bêtise. Et je n'ai que cette caméra-là.
Après, là, elle va bien.
Quoi?
Là, elle est bien. On voit Baptiste à droite.
Mais oui, et c'est quand je...
Mais là, tu sais lire quelque chose, tu n'as pas le message. Reste sur les affiches.
Mais elles sont dans le bon sens.
Mais là, pas. Non, c'est pas dans le bon sens.
Non?
Non, regarde, pas au-dessus du truc, tu as le petit bonhomme à gauche et la flèche à droite, et là, c'est l'inverse.
Ouais, c'est pas normal, parce que normalement, il s'est corrigé. Bon, on s'en fout. Hein. Dans un premier temps, on s'en fout.
Le team, c'est pour les jurys uniquement.
Mais normalement, je vais redonner le lien YouTube aussi, du coup, ils peuvent aller voir la présentation sur...
Mais sur YouTube, ils ne savent pas parler.
Non.
Ouais, donc on s'en fout, en fait.
Donc, ils vont parler par Teams.
Le team, c'est juste pour leur son à eux, quoi.
Ouais.
Tu peux leur dire bonjour.
De la main droite ou de la main gauche, du coup?
Good morning.
Good morning.
Good morning.
Good morning, Siegfried.
Good morning.
Good morning. Quelle année, c'est
Ils en annoncent pour
Tu peux leur dire de regarder YouTube. Rappeler.
Have you checked your mail for the YouTube link? Non, il faut se le PC.
Ah non, il est coupé.
Du coup, ça va empêcher un peu. Hi. Microphone was muted. So.
Good morning, Leo.
Good morning. Have you checked your mail for the YouTube link for the following of the presentation? Because do you see me well here?
Actually, yes.
Okay, that's fine. With the letters in the good sense, or?
I will perhaps also check the YouTube link.
Good morning.
Morning.
Good morning.
Good morning. Daniel, Robin, hello. Morning.
Hello.
Hi, CP. I'll check the YouTube link. I sent just to my partners also. So you will have pull it together.
Là, c'est bon. Maintenant, c'est même pas vrai. On l'a entendu celui-là du coup.
Ok, il est connecté.
Normalement c'est bon. Ouais.
Looks very good on YouTube.
Thank you. Okay, so let's start. Good morning, everybody. Everybody in the room and also everybody on YouTube and on Teams. Welcome for this public defense of the PhD thesis of Mr. Guillaume Bayon-Vicente. So before we start with the presentation, let me introduce the PhD committee who reviewed this PhD work. So the work was supervised by Professor Rudy Wattier and Dr. Baptiste Leroy from the University of Mons. And the other members of the committees were Professor Robin Gosch from the University of Stuttgart in Germany, Dr. Daniel Puyol from University Rey Juan Carlos in Spain, Professor Siegfried Vlaming from the University of Antwerpen, and Dr. Annelies Hanson from the University of Mons, and I'm Patrick Flamand, also from the University of Mons. So before we start, also just for you to have the complete information, Guillaume already has a private defense at the end of October, during which he had plenty of time to have a scientific discussion with the members of the committee. So today we'll give a presentation about his results, a presentation of about 45 minutes, and then we will still have some more time for some additional questions. So Guillaume, the floor is yours.
Thank you. Thank you for these kind introductions. So, dear President of the jury, dear Secretary of the jury, dear members of the jury, dear YouTube, good morning. It's a real pleasure for me to give you this presentation about this 4-year work about the photoheterotrophic production of polyhydroxyalkanoate by Rhodospirillum rubrum. I know that its title sounds a bit barbarian and some complicated, but the aim of this presentation of 40 minutes will be to simplify this presentation in order to make you understand it. And for this, I have to explain you some notions, and I think that the most important one is the subject of the thesis, which is Rhodospirillum rubrum. So, Rhodospirillum rubrum is a bacterium, and bacteria are one of the 3 kingdoms of life, with archaea and eukarya. Archaea are some small microbes that often inhabit extreme environments, such as geothermal springs, permafrost, or hypersaline lakes. Then we have the eukarya, in which, in fact, you find most of the organisms that you know. Animals, so dogs, cats, humans. You have in this group the fungi, so the mushrooms, and the plants. And so Rhodospirillum rubrum belongs to the bacteria kingdom. And I know what you are thinking. Bacteria are dangerous and they are so small that there is no need to study them. And you know what? In one sense, you are right. Bacteria, some of the bacteria are dangerous. You probably know Staphylococcus aureus, that is known in hospital to cause septicemia. You maybe know Helicobacter pylori, that is known to cause ulcer, and some bacteria are responsible of diarrhea or pharyngitis. However, bacteria are also important for our daily lives and for the earth in general. For example, we have tons and tons of bacteria in our gut that constitute the gut microbiota. They help us to digest the different food and to extract the nutrients that are in the food that we eat. In biotechnology, bacteria are useful, and the main example are Artospira, that is known to possess a high content of proteins, vitamins, minerals, unsaturated lipids, and so they are good as food complement. We also know Lactobacillus, that is known to produce yogurt, Acetobacter, to produce vinegar, and in a more uncommon applications, we have Bacillus thuringiensis that is known to fight against caterpillar in cabbage cultures. And as I told you, some bacteria are important for the earth, and we have the cyanobacteria that with photosynthesis produce most of the part of the oxygen that you are breathing, and azobacter and rhizobium that can do some symbiosis with plants and helps them to fix the atmospheric nitrogens. And so in that context, those bacteria are important for the nitrogen cycle. So let's go back to Rhodospirillum rubrum. This bacterium belongs to the purple bacteria group that are found in lakes, oceans, but also most uncommon habitats such as permafrost or geothermal springs. And finally, this is what Rhodospirillum rubrum looks like. So on the top of the slide, you have a typical culture that we are doing at the lab. You can see that it is red cultures. Then on the middle of the slide, you have an optical microscopy, and on the bottom right, you have an electronical microscopy of Rhodospirillum rubrum. If we look a bit more on the name of this bacterium, we can see that this is pink, spirillum, so spirals, and red. So in terms, it's spirals that is red and pink, as you can see on the top left of the slide. So this bacterium is known to use different organic compounds and to use different metabolic regimes, which drives me to the next notion of this introduction, which is the photoheterotrophic and the photoheterotrophic metabolism. So to make you understand what is metabolic regimes, you have to see the cell as a house that is built of red and blue bricks. The red bricks are the carbon, the blue bricks are the electrons, and finally in this winter weather, what you need is something to heat the house, and that is energy. Considering those three parameters, you can have metabolic regimes. We have 4 of them. The first one is the chemoautotrophy, in which the carbon source is the carbon dioxide, so minerals carbon source that is present in the atmosphere, and the energy source are sulfated compounds. Then you have the chemoheterotrophy, in which the carbon, the energy, and the electron sources are organic compounds. In this group, you have some examples, and most of them are known. So you can find in this group all the mammalians and all the animals in general. You have the dogs, humans, and cats. Yes, believe me, that's a cat. Then you have photoautotrophy, in which you can find plants that are known to use the carbon dioxide to extract the carbon, and light as energy source. And finally, you have a mix between those two last metabolisms that is called photoheterotrophy, in which the organic compounds are at the basis of the carbon and the electron source. and where the light is the energy source. And this is the metabolism that is interesting for us today and that performs rhodospirillum rubrum in our conditions. So in order to schematize it, you can just imagine that the food enters in rhodospirillum rubrum metabolisms, and rhodospirillum metabolisms using this different pathway extract carbon and electrons. This is quite easy to understand. For this thesis, we have used volatile fatty acid as carbon sources. So we have acetate, propionate, butyrate, and valerate. And as you can see, there is an increasing number of carbon inside those molecules. Those volatile fatty acids can be found in different fermentation phenomena, such as wastewater treatment plants, cheese whey, brewery, or pepper mill. So this were how rhodospirillum rubrum is extracting the electrons and the carbon. Let's see how energy is extracting from the light. So the light means that rhodospirillum rubrum can use the sun or artificial light as soon as there is some photons that are harvested by what we call light harvesting complexes. Those complexes are composed of pigments such as carotenoid or bacteriochlorophyll. The aim of it is to drive the energy to a special pair of bacteriochlorophyll that is present in the reaction centers that will generate and release one electrons that will go from intermediary to intermediary that are kinones, bacteriophytin, or cytochrome. At the end of this cycle, some electrons are released and accumulate inside the periplasm. The periplasm is the space that is present between the membrane that is facing the outside of the cell and the one that is facing the inside of the cell. Those protons will accumulate and generate what we call a proton gradient that will be pumped by an enzyme that is called ATP synthase to produce ATP. That is the fire of the house, and so the energy. So now we have seen how those three elements were extracted from the carbon source and the light. Let's emphasize a bit on electrons because it is an interesting features of this thesis. So you have to know that in rhodospirillum rubrum metabolisms, as in every metabolism, so in every cells, there is metabolic reactions that allows the conversion of, in this case, compounds A into compounds B or B into A. This metabolic reaction is catalyzed by an enzyme, which is in this case called enzyme AB. What is interesting with metabolisms is that sometimes those reactions requires another type of molecules that are called cofactors. Those cofactors can exist into two forms. The first one is the oxidized forms, and the second one is the reduced form. The reduced forms is the most common form of electrons in the cell. And what is interesting with those two forms is that it exists a balance between the oxidized and the reduced form that is mandatory for the metabolisms to optimally function. As soon as environmental factors disrupt this balance, which is in this case means that there is a lot of reduced cofactors, this balance has to be reestablished using different metabolic reactions. In this case, as there is too much reduced cofactors, it means that some reduced cofactors will be consumed by metabolic reactions. And so in this case, the cell will use the conversion of A into B to consume those reduced cofactors and reestablish the optimal balance. So this was for simple reactions in the metabolisms. However, in metabolism, reactions are occurring successively in what we call pathways. And so the features that I've explained just before is correct and valid for and has to be implemented for pathways. So in the case of the blue pathway on the left of the slide, you can see that there is a pathway in which two reduced equivalents are produced, which means that this pathway is known as reduced equivalent producing pathways. In the middle of the slide, in yellow, you have a pathway in which one reduced equivalent is produced, whereas one is consumed. This pathway is known as reduced neutral pathway, as there is no reduced equivalent that is produced. And finally, you have on the right of the slide, a pathway in which two reduced equivalents are consumed, and so those pathways are called reduced equivalent consuming pathways, or redox sink, electron sinks. So I will go to the explanation of polyhydroxyalkanoate, but just keep this last notion in mind because it will be important for the rest of the presentations. So I don't have to remind you all the negative effects of petroleum-based plastics. You know that this is highly pollutant for the environment and that they are responsible of the death of several animals. But maybe something that you don't know is that the mechanic destruction of plastics can lead to the accumulation of microplastics and accumulation of those microplastics in filtrating organisms such as mussels, oysters, or some echinoderms. And you know that we are eating those organisms. And so we are facing some problems and some unknown effects of those microplastics accumulation in our body, and we don't know for the moment the consequences on our health. All of that to say that it is important to find some alternatives that are the polyhydroxyalkanoates. Those polymers present some physicochemical properties that are close to petroleum-based plastics, but present the advantages of being biodegradable and exhibiting a broad range of applications such as surgery, agriculture, packaging, or drug delivery. But concretely, what are polyhydroxyalkanoates? So polyhydroxyalkanoates, or PHAs, as we named it in the lab, is a polyester family from which the properties depend on the monomeric sequence, which means that here in the middle of the slide, we have an archetype of PHAs in which you can see that there is a radical. This radical can be changed and into with some different chemical groups, and in this case we have a methyl group that can lead to the production of polyhydroxybutyrate. We have an ethyl group which is responsible of polyhydroxyvalerate, and finally we have a propyl group which lead to the production of polyhydroxyhexanoates, and so on and so on. What is interesting with polyhydroxyalkanoates and what makes them interesting for the bioindustrial application is that we can have different type of polymers. You can have homopolymers in which all the monomers of the polymer are the same. So in this case, you have polyhydroxybutyrate, 100% polyhydroxybutyrate. Or you can have some copolymers in which you can have successive monomers that are in the polymer. So here you have an hydroxybutyrate, then 2-hydroxyvalerate, and finally 2-hydroxyhexanoate. What is even more interesting with copolymers is that the sequence of the monomers inside the polymers is really important to make vary the physicochemical properties of the total polymer. So this was for the chemist part of the PHA's production, but what is interesting for us is the biological significations of polyhydroxyalkanoates. So those polyhydroxyalkanoates, or PHAs, are accumulating inside granules that are formed of phasins. Those granules are all the white bubbles that you can see inside the cell. In literature, they are considered as stock of energy, electrons, and carbon when another nutrient is limiting. So those nutrients are nitrogen, sulfur, or phosphorus. So to sum up, it means that the bacteria are accumulating PHA when the conditions and the environment is too harsh to lead to the production of biomass. In that sense, it will accumulate PHAs and so accumulate the carbon in order to not losing it, and we will mobilize it when the conditions and the environmental conditions are good again. However, this last feature is not correct for us because we have observed this PHA production under non-limiting conditions. And so this is where my thesis began, because the aim of it was to find what in these metabolisms can drive PHA productions. And believe me, it is like looking for a needle in a haystack. You find it? No? Welcome in science. One of the hypotheses that we had is that polyhydroxyalkanoate production is driven by an excess of electrons. As you can see in this pathways, which is the pathway for the production of polydioxybutyrate in this case, you have a net consumption of 1 reduced equivalence, which means that this pathway can be considered as a reduced equivalent consuming pathway or an electron sinks. But what in our environmental condition can cause the production of a high amount of electrons? The first hypothesis that we have is that the carbon source is responsible of the generation of electrons, and this is quite easy to understand, because I told you that during photoheterotrophic productions growth, the carbon source was responsible of the release of carbon but also electrons, which means that different carbon sources are responsible of different yield in terms of electrons generations. This is for the easy part. But then we also think that the light intensity and the light in general, so the photosynthesis, can also be responsible of the production of some reduced equivalents, the NADH. Indeed, I told you that in rhodospirillum rubrum, the photosynthesis is responsible of the generation of some protons that are accumulating inside the periplasm. In normal case, those protons are pumped by the ATP synthase to produce ATP. However, what I didn't tell you is that some protons can also be pumped by an NADH dehydrogenase to produce NADH, and so to produce electrons. So to sum up those two hypotheses, what we have is that we have some environmental factors that disrupt the balance between oxidized and reduced cofactors that yields a redox stress. This redox stress is in favor of reduced equivalents that so as to be consumed through reduced equivalent consuming pathway or electron sinks. And we believe that PHA production is one of these electron sinks. So as everything is understood for everyone, we can go to the result part of this thesis. So the first strategy that we have is to use volatile fatty acids because they are known to produce a lot of electrons. So the volatile fatty acid that we will use is named valerate because it is the one that is known to produce the more electrons. So we have used these volatile fatty acids. So you will see on the for the result part that on the left of the slide you will always have a sketch of a cell that is simplified for the need of these presentations. So in this case we have used valerate that is uptake by the cell and then assimilated through the central carbon metabolisms. As we have already seen, the central carbon metabolism is known to produce carbon that will be directed to produce some biomass, but also some electrons that will that will join an electron pool. The idea with this part of the results is to make a description of the electron balance inside this electron pool that will drive the electrons for PHA productions. That's the main idea of this part of the thesis. Using these techniques, we have observed a PHA production of 15% of the dry weight as PHAs. The graph on the right will be a typical graph that you will see all along this thesis presentation, in which you will see the PHA content in y-axis that is plotted against the time in y-axis. And you can see that we have maximal production of after more or less 40 hours of 15% of the dry weight. It was quite a decent production of PHAs, but it was not as much as we expected regarding the different electronic microscopy that we have. So we decided to go further and to conduct some phenotypic and proteomic analysis. And we have seen using those techniques that the carbon dioxide supplementation was mandatory for the growth of rhodospirillum rubrum in the presence of valerate. Indeed, you can see here on the right a graph that depicts the growth of rhodospirillum rubrum that is expressed using the optical density. And you can see that in red, when low concentration of bicarbonate ions are supplemented, implemented to the medium, you can see that there is an incomplete growth, and that the growth is complete with the blue lines with an excess of bicarbonate ions. So we have tried to add some bicarbonate ions during the growth, and we have observed that as soon as we added the bicarbonate ions, we observed a complete growth of Rhodospirillum rubrum. So using some proteomic analysis, we have found that this carbon dioxide was fixed by the cell using the Kelvin-Benson-Basham cycles. And you say, what is the point with it? The point is that this cycle is also known as an electron sinks. And so both pathways, Kelvin cycles and PHA production, will compete for the same role in the cell, that is the electron sink role. And so in that frame, when we use valerate as carbon source, the electron pool will be divided into first the Kelvin cycle and secondly the PHA productions. In order to counter this effect, what we have tried to do is to progressively to reduce the bicarbonate ions concentration and to progressively add it in the cell. We have done it in order to reduce the flux of the electron to the Kelvin cycles, and so to reduce the flux and to maximize the flux of electrons to the PHA production. And using these techniques, we have observed a PHA production of more than 20% of the dry weight, which represents an increase of 50% of the total PHA content. A last thing that is interesting to see with PHA production in the presence of valerate is that we obtain a copolymerase of polyhydroxybutyrate, co-hydroxyvalerate, with a high monomeric content of hydroxyvalerate, which is really interesting for the bioindustrial applications. So the second hypothesis that we wanted to test is the use of different light regimes. So for this we have two kinds of experiments. The first one is the experiment that we called light stress. In this kind of experiments, bacteria were cultivated in the presence of 50 micromolar photons, and as soon as the growth is observed, so as soon as the OD reach a defined OD, we increase this light intensity from 50 to 150 micromolar photons. So typically, what does it mean is that during the beginning of the growth, there is a classical flux of protons that are harvested by last light harvesting complexes, and as soon as the growth is started, we increase this light intensity to induce a massive influx of photons to saturate the light harvesting complexes that will thus induce a maximal activity of the reaction centers and thus release the maximal protons. In that frames, protons will be pumped by ATP synthase, but also by NADH dehydrogenase to produce the protons, the electrons that are interesting to produce PHAs. So we have compared the PHA productions between the bacteria that were submitted or not to the light stress. So this is for in the case of bacteria that were not submitted to the light stress. You can see that we are using acetate as carbon sources because this carbon source is the less reduced carbon source that we have in terms of volatile fatty acids, and because this carbon source is less dependent to bicarbonate ions, and so we can just simply remove this parameter from the equations. So under normal conditions, so 50 micromolar photons, we still observed production of PHA linked to electrons that are produced during the photosynthesis. But we observed a production of 100% polyhydroxybutyrate reaching 35% of the dry weight as so PHB. However, when we increase the light, so we increase the light intensity to increase the amount of protons that are present in the periplasm, we observed that more electrons are joining the electron pool, and that the PHA production observed in these conditions is reaching 50% of the dry weight as PHB. So this increase in PHA production also represents an increase of 50% of the total PHA content. However, we have conducted some proteomic analysis to compare the cell before and after the light stress. So we extract the proteins and we see if the abundance of certain proteins were higher after the light stress. And we observe that some proteins of the isoleucine biosynthesis pathway were overexpressed after the light stress. We would like to be sure of this result and to go further. And so we have studied the isoleucine content in the cell for bacteria that were not submitted to the light stress and the one that were submitted to the light stress. So in blue you can see the growth of the bacteria, and in red you can see the isoleucine content. You can see that when bacteria are not submitted to light stress, the isoleucine content remain constant over the growth, whereas when we submitted Rhodospirillum rubrum to light stress, we observed an increase in isoleucine content. And you will say, what is the point with this isoleucine biosynthesis pathway? Indeed, this pathway is also hypothesized to act as another electron sink in the cell, which means that once again, when we submitted our bacteria to light stress, we suspect that some electrons are directed to isoleucine biosynthesis pathway, and the other electrons are used to produce PHA, which means that in this context, both pathways are once again competitor for the same role inside the cell, which is the electron sink role. This aspect of the thesis will have to be studied further, and I will leave the floor to another PhD student to do it. So after that, we have studied the effect of different light intensities, but this time we have submitted the Rhodospirillum rubrum from the initial to the end point of the growth. We have submitted Rhodospirillum rubrum to different light intensities, ranging from 9 to 150 micromolar photons. We have first conducted some phenotypic analysis, and we have observed that there is no difference, so no significant difference in the growth curves so in the growth rate or in the shape of the curves with regarding the different light intensities. However, when we have studied the PHA content that we have observed in Rhodospirillum rubrum under those different light intensity, we have observed that PHA production was higher with light intensity higher than 38 micromolar photons, which means that we have observed a significant higher PHA content with in bacteria cultivated under 38, 75, or 150 micromolar photons square meter seconds. This was a really interesting result because it means that we do not need to increase the light intensity to obtain a high PHA production, which is interesting regarding the energy part in total production cost. After that, we have tried to apply the different concepts that we have demonstrated during this thesis in the presence of a mix of VFAs, because we obviously know that during fermentation phenomena, VFAs are not coming one by one, and they are coming as a bulk of VFAs. The first thing that was interesting to observe is that acetate and propionate, which are the smallest VFAs, are assimilated first, and then when there is no more acetate or propionate in the medium, butyrate and valerate are assimilated. Regarding the PHA production, we have thus conducted some experiment in which we have decreased the bicarbonate ions concentration and in which we have applied a light stress. And what was intriguing is that there is no effect of those elements on the PHA production observed in presence of a mix of VFAs, which is a bit intriguing. And so this part of the thesis has to be studied further in order to understand what is happening. We have here demonstrated that there is a kind of synergic effect in the presence of a mix of VFAs, but we do not understand how this synergic effect is happening in the cell and what is the impact of this synergic effect on the electron pool. So what can we conclude about this thesis? The first thing that we can conclude is that it is easy to change the PHA content and the type of the type of PHA that we can produce in a rhodospirillum rubrum using two parameters. The first one is the type of volatile fatty acid. We have found that using different volatile fatty acid, we have different type of monomers. We have demonstrated that the content, so the quantity of PHA is different regarding the different volatile fatty acids that are used. And the second thing that we have demonstrated is that playing on light intensity could represent a good strategy for playing on total PHA content. The common features between those two parameters is that they are known to induce a disruption of the intracellular balance that can thus drive PHA productions. And so we have here some different clues that PHA production in rhodospirillum rubrum is driven by the redox balance. Regarding the perspectives of this thesis, first the fundamental perspectives. We have here, I think, answered a lot of questions, but there is still a lot of questions that have to be answered. I think that the first one is and the most interesting one is the implication of isoleucine biosynthesis pathway in rhodospirillum rubrum, and more precisely in redox homeostasis. We have here demonstrated that clearly there is a link between light intensities and isoleucine biosynthesis, but it will be interesting to prove this aspect of the thesis. A strategy to do it is to build a method in which one of the enzyme, so one of the gene coding for one of the enzyme of the isoleucine biosynthesis pathway can be deleted, and see how the cell react to the deletion of this enzyme, and what is the impact on the different PHA productions. So the second thing that is interesting to study is the synergic effect that we have observed in the presence of a mix of VFAs. So what is the impact on the biomass? What is the impact on the central carbon metabolisms? What is the impact of this mix on electrons pool? And finally, what is the impact on PHA production? So considering and concerning the industrial perspectives, I think that we have here clearly demonstrated that rhodospirillum rubrum could constitute a good candidate for biotechnological applications. One of the most obvious biotechnological application that we can do is to use some fermentation phenomena that are producing VFAs and to directly feed rhodospirillum rubrum with those VFAs to produce PHAs. But honestly, we know that this process is not economically feasible, and it is more likely to consider rhodospirillum rubrum as a biorefinery in which we can use different parts of rhodospirillum rubrum. In that context, we know that rhodospirillum rubrum is producing PHAs because we have demonstrated it here, but we also know that rhodospirillum rubrum is producing some carotenoids and in general some pigments that could constitute some good co-products. We know that rhodospirillum rubrum can produce fertilizers and some biomass to feed some shrimps or fish. And I think that using those four co-products, so those four compounds, if I can tell it like this, we can make this process economically feasible. So I would like to thank you for your attentions, even if I don't know if you were attentive during these presentations because you are on YouTube. I would like to thank the members of the jury for their kind reading of the thesis and their kind remarks during the private defense. I would like to thank Maternova groups for their support. And finally, I would like to thank the Protmi group and more particularly Professor Rudy Wattier and Dr. Baptiste Leroy for their kind support during this thesis. Thank you very much.
So thank you very much, Guillaume. Now we can start with some
questions.
some more questions. So maybe Professor Ghosh, you can start with the discussion.
Okay, can you hear me?
Yeah.
I'm getting this. Can you hear me?
Yeah.
Yes.
So it's not a big deal.
Là, je comprends plus. Là. Vous n'avez pas un câble Ethernet pour vous?
Maybe a small. There is a lot of echo.
Yes.
Maybe to close down a YouTube. Yeah, I've already closed YouTube actually.
Ok, on close YouTube?
Non, je voulais dire parce que lui.
Ah, ok.
Can you hear me better now?
Yeah, can you speak loudly, please? Louder?
Yes. Can you hear me now?
Yeah, it's quite good for the moment.
Yeah, it's okay. We can hear you.
Vous avez allumé votre micro?
Just
Micro est allumé?
if it's not being clear. So again, it was a very nice presentation, which I enjoyed very much. It was very clear and gave a nice overview of the whole area. So I just checked my watch. Everyone can still hear me, I hope. I want to ask you, as a first question, I want to ask you about stress. Can you explain to me, you've talked about redox stress, but redox stress is kind of a complicated concept. Can you explain to me when rubrum grows under various kinds of conditions, what do you understand by oxidative stress or photooxidative stress in terms of its metabolism and effect on the photosystem?
Yes, so the first part of the question was about the redox stress. So in the case of Rhodospirillum rubrum cultivating under photoheterotrophic conditions, the redox stress is the dysregulation of the intracellular redox balance. So it means that typically if you have an excess of reduced equivalence, it will induce a redox stress that has to be cope with different elements. The second part of the question was the oxidative stress, and more precisely the photooxidative stress. This type of stress is mainly encountered during growth in the presence of under photoheterotrophic growth in the presence of oxygen, which is a really typical case, because it means that the oxygen tension has to reach and to be higher and to be higher than 0.3%. And in this case, what we heard about photooxidative stress is the generation of singlet oxygens by the excitated bacteriochlorophytes. So it is the I would say contact between those two elements, so oxygens and excitated bacteriochlorophyte.
Okay, let's stay there a second. That's correct. Singlet oxygen is important in photooxidative stress. But maybe you can make that a little bit more precise. Of course, we have two photosynthetic components which contain bacteriochlorophyll in photosystems. So when I think of the really very strong effect of photooxidative stress, which photosystem do you think is being attacked most strongly?
So which photosystems is the
photosynthetic component?
Okay. I know that the carotenoids can help in these situations by just dissipating the energy of bacteriochlorophyte and the energy that is present in this special case. Is it what you mean?
Yes.
Okay.
Yes, but we have two photosynthetic components. One is the light harvesting complex, which is harvesting light.
Yeah, and the one, yeah.
And the other one's the reaction section.
Mm-hmm.
Yeah. So, I mean, do you think can we understand, in terms of the primary photooxidative stress which the organism is experiencing, which component is probably the most sensitive?
I would say that it is the reaction center because it is where the bacteriochlorophyll is excitated.
Yeah, that's correct. Okay, so let's think of this a second. Even when oxygen is not present, there is still a photosynthetic light stress. Even the absence of oxygen, what might that light stress be?
I would say that it is when there is too much light and that the bacteriochlorophyll is not able to relax in those cases. But I know that so most of the purple bacteria can just modulate the amount of photo systems, so light harvesting complexes, in order to reduce this stress.
Yeah, but this is not true of ribbon. Ribbon can't do that. The composition of the membrane is always constant.
Yeah.
When we think of light stress, you're correct. I haven't quite got to the point yet. So if we increase the light intensity, the photosystem becomes saturated. And when it's saturated, it's producing an oxidative stress. What is the oxidative stress, which we understand? If you increase the light stress to high levels, photosynthetic growth is basically reduced. It's reduced. So what is that stress, actually? What do we understand about that stress? In a way you said from the talk, I just want to hear you a bit more explicitly.
Light. So bacteriochlorophyll enters in excited form, and after that, what is happening? I don't know, honestly.
Because when you have very high light levels and you have a limited amount of photosynthesis, then you're producing an excess of redox equivalents, right? So your redox equivalents.
Yeah, but this is what we call redox stress.
Taken away by dark metabolism.
Yeah.
They will generate a very high proton-motive force and stop the metabolism. Okay, so if we sort of move to what you were saying about the PHA production, I noticed that in your initial work, I think the time frame for the photosynthetic metabolism, where you were producing the maximum amount of PHA, was at about 50 hours. And then later on, your maximum, which you mentioned.
I think that this is 20 hours. No.
Sorry.
I think that it is 20 hours. No.
On your diagram, I thought I saw 50 hours actually. 20 hours would be very quick. Right? It would be. Probably ribbon takes with acetate. I'm not so 100% certain, but normally photosynthetic growth takes about 7 days to reach the maximum intensity, the maximum amount. But some of your PHA production was much longer time actually. At particular highlight intensities. So, do you think, in terms, were they simply stressed with light and couldn't remove the redox equivalents and then shunted that into PHA, or did you look at the actual growth of the culture? But sometimes the culture doesn't seem to be growing, but the cells get longer.
Yeah,
that's also a possibility. So what do you think is, there were different time frames in your effective light intensity. Right? So how do you interpret that?
It's quite a tough question because we have observed this type of reactions for acetate competent strains in which we never demonstrated, but we have already observed that in this strain was longer than the wild type strain. So definitely I think that there is something with the length of of the bacteria, I think that Rhodospirillum rubrum is reacting in two times. I think that there is a quick response to quickly consume the different reduced equivalents that are produced by the photosynthesis, and after that there is a more longer and slower response that consists of adaptation of the strain to the light intensity.
Yeah, that could be the case. That's an interesting point. When you mentioned at the end, you were talking that isoleucine metabolism, you think, is very central to this whole story. Now, one of the things we know is that when the light intensity increases, that the photosystem is actually diluted out. It seems to get less to a lower level when you have low light intensities. So what we do know is that rubrum is full of membranes. It's full of membrane proteins. Many of the membrane proteins are full of isoleucine as well.
Okay.
So do you see any correlation between, could you imagine that the isoleucine is maybe connected to, is there a correlation to the amount of membrane, or how do you imagine that? Where is the what is this? I'm really trying to get to the point. What is the physiological sense of using isoleucine as a reservoir?
Honestly, I don't think that I can answer these questions. I can just throw some hypotheses, because we have already explored the PPG-PP correlation with isoleucine biosynthesis pathways, and we didn't see anything. But I remember of a publication in which they have compared and correlate the isoleucine content with the photosynthetic activity or membranes. So I guess that there is a sense into it. But the isoleucine content that we have in this disease, I think that we have mainly quantified the free isoleucine, and I don't think that they are incorporated into some proteins that can be present in the photosynthetic membranes.
Okay, right. Another question is, when you looked at the CO2 utilization, where you increase the bicarbonate to get higher pHs, you probably did a series of experiments, but it seemed to me a very big jump from 3 millimolar to 50 millimolar. When I look at the growth rates, there's not a 20-fold increase. It's only a small increase, really.
Yeah.
So what about the intermediate concentration? Is there a kind of a jump between 3 and 5, or is it continuous? What's that look like?
Now, to be honest, 50 millimolar of bicarbonate is the classical bicarbonate concentration that we are using. So it is typically our control condition. And after that, we have observed that when we reduced and when we just delete bicarbonate ions from the cultures, there were an impact. But I think that when we have done this 3 millimolar experiment, and when after we added some bicarbonate ions, I think that we just added twice. So it means that Rhodospirillum rubrum needs only, if I can say it like this, 9 millimolar of bicarbonate ions. So yes, typically there is way too much bicarbonate ions in our medium, which can explain the reduced pH content that we have.
If you were to do this industrially, how would you do this? I mean, if you would add then sodium bicarbonate, or how, if you were doing on a very large scale, how would you do that?
I don't know. I think that there are some compounds that are used and that can just solubilize, evaporate, make the bicarbonate ions goes into its gaseous forms, and so we can think about this solution to decrease artificially the bicarbonate ions concentration that are present in those effluents.
Okay.
But maybe discuss with Professor Vlaming, that he will be more an expert in this domain.
I just want to ask you again about light intensity, the light intensity quality. We've already talked about this before.
Yeah, numerous times.
I think you told me you were using halogen lamps, and you talk about 9 to 150 micromoles of photons per square meter per second. But not all of the light can be utilized, of course, by the halogen lamp. So how do you see which regions of the light intensity can be really used by the photosystem? I mean, your 150 micromoles photons is presumably the total number of photons which your light meter is measuring, right? It's not the utilizable.
Yeah, sure.
Which regions of the spectrum of the halogen light do you think can be used by people?
So we have the region between 390 and 420 nanometers that correspond to the Surrott bands. Then we have the part of the light emission spectrum that is harvested by carotenoids between 450 nanometers and 550 nanometers. Then I think that we have the one between 600 and 650 for the bacteriochlorophyll, for the first band of bacteriochlorophyll, and finally the one between 800 and 880, if I remember well.
Yeah, that's right. So how many, if you add up those regions, how many micromole photons do you think are really physiological?
So I've done the computation of this, and if we take, for example, the 50 micromolar photons light intensity, only 1/3 of this light emission spectrum is actually harvested by rhodospheral rubums, which means that we can decrease this light intensity. But I mean, the effective light intensity that is harvested is about 17 or something like this.
And again, if you were to do this industrially, how would you, what kind of setup would you think would be industrially possible for illumination?
Maybe we can think about some filters to specifically choose the wavelengths that are used. We can change the lamps to go through some tungsten lamp. And we can, I don't know if it is possible, but design some lamps that are emitting specific wavelengths to the emission, the absorption spectrum of rhodospheral rubrum. But I don't know if it is economically feasible. And
okay, I think I'm keeping an eye on the time. I think I've more or less exhausted my time. So I think I've got most of the questions I wanted to ask you. Just the last question. When you were, you mentioned when you go through the growth phase with different amounts of CO2 and light intensity. You see a total change of the dry weight, the pHP, but you see also relative changes, like in some conditions the photosystem has been reduced drastically or increased drastically. What are the fine details of that?
so in the case of bicarbonate ions in the presence of valerate, is it the question?
Yeah, of course.
I don't think that we have checked the photosystems to compare the 50 micromolar photons and 3 millimolar photons.
And the high light intensities, was the photosynthetic membrane decreased, or you see that from the color even a little bit, or you don't know?
I don't remember. The only data that we have for this is for the light stress and the different light intensities in the presence of acetate. And yes, we have observed that after the light stress, the light harvesting complexes were decreasing, which was normal for us. I mean, when we increase the light intensity to react.
Yeah, very last question. When you take your light stressed organisms with a high PHA, which have grown up, and you re-inoculate them, do they grow immediately, or do they have a long lag phase, or what happens there?
Yeah, that's typically the next step of the fundamental work with rhodospelum rubrum. We have observed this kind of phenomenon with acetate, so we guess that we will observe it with light stress. But yes, that's an interesting perspective.
Okay. Thank you. Those are my questions.
Thank you.
Thank you very much, Professor Ghosh. Maybe Dr. Puyol, you can continue with the questions.
Sure. Thank you very much. Thank you, Guillaume, for your brilliant explanation about your thesis outcome during this last year. Before anything else, I would like to express my gratitude to your thesis directors, Reddy and Baptiste. It's just a pleasure for me to be here as one of the thesis committee members. And this thesis is really a good example of a well-structured and well-focused, novel, interesting, and the most important thing is a timely study. It's a quite complete and include a brave analysis that never were there, as the case of valerate as a potential source for polyhydroxy valerate production. You and of course your thesis directors deserve my congratulations. I really enjoy reading the final manuscript and learn a lot, as my expertise is not so specific in metabolic mechanisms, and this is key for optimizing biotechnological applications in field scenarios. However, I have some comments and questions, and as well as some curiosities regarding the work. For example, we observe in real applications that it seems to be some competencies between several carbon allocation mechanisms. You have already presented most of the metabolic mechanisms of purple bacteria that affects the accumulation of PHA. However, despite you have mentioned glycogen in chapter 7, it's not clear how glycogen might affect the accumulation of PHA. So I was wondering whether glycogen may be a competition for PHA accumulation. So what do you think?
Okay, so the aim of glycogen quantification in chapter 7 was not to see if those two carbon stock can enter in competition. The aim of it was to emphasize and to go further with the proteomic analysis. So we have seen that there is some proteins of the glycogen productions and mobilization that were affected by the light stress, and so we decided to go further in that sense, which finally didn't result in anything because we didn't see any change of glycogen content. But fundamentally, I think that there is something, because they are both considered as carbon stocks, and so ultimately they will compete for the same feedstock. I think that PHA is favored in our conditions because VFAs are more closely to produce PHAs, or they are sharing some metabolic reactions, which is not the case for glycogens. However, I think that if we have used some sugars instead of VFAs, maybe the idea will be different, and that glycogen will be favored.
Okay, so we may say that a low carbon content substrate and high light stress will just go better for PHA production, and other conditions would be better for glycogen accumulation.
I don't know, because I never tested, but I would be curious of testing the light stress on rhodospelum rubrum when assimilating some sugars, to see if there is a comparable effect of the light stress on glycogen content. But honestly, I don't have any expertise on it, but it will be interesting to test it.
Yeah, thank you.
Thank you.
And also, I have another question. This is a different story. It's something related to what Robin has commented. It's regarding the spectrum of the halogen lamp that you have provided. So you have explained a bit the basis for choosing this lamp. But yes, as Robin has commented, the Clostridium rubrum and most of the bacteria are mostly active at the near infrared light range between 800 and 865 nanometers. That is the most active part of the light that they can use. And also, this is not there is no competence for this light source with another photosynthetic microorganisms. So I think that is just my first comment is that it seems that not the best light source for the experiments that you have used. Just for the having enough light for the metabolism, but also it's an interesting light source because you know that even if your spectrum is not completely useful for the bacteria, you know that the spectrum where the light can cause stress is much wider. So, for example, you know that the light, the part of the light spectra that causes most stress is the blue light, and your lamp has a lot of blue light. So maybe you are not putting a lot of energy for the bacteria, but you are putting a lot of stress into the bacteria. So that for the objective of causing light stress, then maybe was a good choice, but maybe not the better for
the growth. Yeah.
Production.
Yes, I agree with you, and I think that Professor Gosh is currently studying the link between blue light and near-infrared absorptions. But yes, definitely it's a great features, and yeah, so it's quite a chance. We were a bit lucky, I think, that our halogen lamp was so exciting in the and emitting in the blue spectrum.
So in this sense,
Faut mettre le chargeur.
Faut
mettre le chargeur. Le chargeur.
LEDs for growing bacteria. So you expect that you will have the same light stress when you use near infrared light?
Regarding the light stress, I think that we can obtain the same thing, because when we will use near-infrared wavelengths, we will definitely excite the bacteriochlorophyll and so the reaction centers, and we will ultimately produce some protons. So if we overexcite this reaction center, we will produce the same effect. So we will have more protons, and if we have more protons, we will trigger the reverse activity of NADH dehydrogenase, and so we will produce electrons. So I guess that we will have the same effects. But sometime with biology and with microorganisms, we didn't know.
Well, this is not exactly correct, because you know that the light is composed by photons, and the photons has different energy, depends on the wavelength. So even if you have the same amount of photons, you are working on the near infrared range, then the photons contain less energy, and probably they will cause less light stress.
Yeah,
blue photons, for example.
I didn't say that we will use the same light intensities, but I think that if we try to reproduce what we are doing here, so we can find an optimal near-infrared emissions for the growth, and then just increase it to induce this production of protons. So I don't think that the light intensity that we have observed in this thesis will be good for the near-infrared experiments, but I think that we can reproduce the same concepts.
Yeah, yes, in different balance, but same concept.
Yeah.
Thank you.
Thank you.
Also, you propose, just to change completely the question, you propose to tune your photobioreactor to selectively produce PHA with a specific monomer composition. This is really interesting. This is just one of the first time that I see this in a specific experiment. However, I will have a big doubts about how this can be possible. This is just in the same line that what Robin has commented before. So theoretically, you may solve your BFAs from a fermentation broth, right? You can just ferment your feedstock mostly composed by proteins and sugars or whatever, and then the fermentative bacteria can produce the volatile fatty acid that the purple bacteria can use for producing PHA, for growing, etc. But during the fermentation, you know that the fermentative bacteria produce a lot of carbon dioxide, and most of this carbon dioxide will remain in the water, so they will be dissolved in the media. So you have checked that CO2 is a killer for PHA production, as it promotes growth instead of PHA accumulation. So how could you promote the PHA production in a real system?
Yeah, it joined the question of Professor Ghosh. I don't have any idea of doing it. I think that there is some system that has to be that should exist. I propose that there is some compounds that can be added in the bioreactor to make the bicarbonate ions goes into their gaseous forms. But honestly, I have no clues of if it is possible or not.
But you gave answer to this in your thesis. So it's just promoting the other ways that you have demonstrated to enhance the PHA production. Just to promote the other stress situations, just not related to carbon dioxide, because the carbon dioxide is just related to growth and in the Calvin cycle, and so if you just promote other stress situations, then the carbon dioxide has no effect on this.
Yeah, maybe we can think about incorporating another compartment in the bioreactor, just before the bioreactor, that with a bacterium that is known to consume carbon dioxide. I could think about some cyanobacteria that will just, and so the output of this bioreactor will be enriched in VFAs, but not in carbon dioxide. Maybe a stupid idea, I don't know.
There is no stupid idea, it's just only a hypothesis that has to be proved. Okay, yeah, thank you. Another question is the effect of light stress on the PHA production. The potential of this is very interesting. In some of the figure of your thesis in figure 7.7, you so clearly this key result from your thesis. So increasing the light stress obligate the cells to accumulate the stress of the reductants in form of PHA, even during growth conditions. This is the main difference with other kind of PHA accumulator bacteria. That yes, they are just producing PHA in response to the excess of the reductants in non-growing conditions, because here you have light and you can obtain energy from light.
Yeah.
So for artificial irradiated systems, this can be used for enlarging the PHA productivities. However, you know that we are mostly moving towards sun irradiated systems. So how this can be useful in a sun irradiated photobioreactor? So you have any idea?
I didn't understand the questions. What can be used for the bioreactor?
So you know the light stress increase the PHA production potential. So you put more light, then you have more PHA.
Yeah.
But then you can tune your light intensity in an artificial light irradiated system, an artificial bioreactor system. But in a real sun irradiated system, you cannot control the sun.
Mm-hmm.
So how you can use this for a sun irradiated photobioreactor? So you have an idea, any kind of configuration or?
Yeah. One of the ideas will be to use the sun to illuminate the bioreactor. So, for example, in a raceway ponds, and as soon as we have a kind of biomass production part of the raceway ponds, and as soon as we enter in a kind of PHA production part, we can put some LEDs, so near-infrared LEDs, in this part just to artificially increase the light at this particular point of the bioreactor.
Yeah, well, this could make sense from a theoretical point of view, but artificial light in open systems this is not to be very, very economically good. So maybe, I don't know, this is a really problem that we are experiencing when we are scaling up the systems. And this is not an easy question. So just only a curiosity if you have any idea about this. So, but we will continue working on that.
Okay.
Also, in regard to this, I just you propose a system in Figure 10.3, and I have a bit doubts about your system. The main problem that in your system is that you know that the potential adaptation of the culture, open pond, and also another problem is the very likely proliferation of other bacteria, both photosynthetic as well as chemosynthetic bacteria. So this likely will affect a lot the dynamics of the BFAs. And also some PPD species have the ability of using the glyosylate sand and will be complete. The mechanism will be totally different, especially in the use of BFAs. Also, some chemotrophic species may feed on the reduced BFAs, especially if there are inorganic electron sinks like oxygen, nitrate, sulfate. So your proposed system will be only feasible for pure cultures, which is not the case in open ponds.
Mm-hmm.
Just a comment that your thesis is very fundamental, but now this is for engineers and the people that are working on how to put this amount of knowledge into practice. This is really challenging,
I guess.
Because would be just to build and bridge some to build some bridges between the fundamental knowledge and the real applications. So this is not a question, but just it's a recommendation that I just make to you again, as in the defense. So I will just encourage you to move towards mixed culture biotechnology, because this is really challenging. So you cannot control everything in a mixed culture biotechnology. So in any case, as I comment, this is not decreasing the merits of the thesis, as the basis for further understanding of the process relies on works like this. So this is just only a comment. So you have any comment about this?
Yeah, I guess you are right. I mean, you have more expertise in this domain than I. The aim of this thesis, as you tell it, was more fundamental. But yeah, I guess that mixed purple bacteria, a culture with mixed purple bacteria is more economically feasible, and we don't have to spend some money to just check the axonicity, and yeah, it presents numerous advantages over the pure culture. So I kind of agree with you.
Yeah. Okay, thank you very much, and I again congratulate you for your brilliant thesis, and I desire you the best in your brilliant near future.
Thank you.
Thank you.
Thank you.
Thank you very much. Professor Vlaming, you can continue.
Thank you, Mr. Chairman. Can you hear me?
Yeah.
Yes.
Yep.
Excellent. Guillaume, my congratulations. You have delivered a great piece of work. You worked hard and you went deep, and you created lots of novel insights. This is very nice. Also, congratulations to your supervisors. It's very informative thesis, a lot of original works, and then today, and also last time, but you have shown your didactic skills, and you have very clearly presented and very accessibly presented your work. So that is really nice to communicate also so well. I have the luck to follow a number of very experienced and expert jury members, taking lots of very good questions. So I need to improvise a little bit. But I was puzzled about your response on sunlight versus artificial light, because you say then I'll add a bit of artificial light. But how does the flux intensity of sunlight compare to artificial light? What micromole per square meter per second are we getting in full sun?
Yeah. So how much? What is the light intensity of sun? Typically, that's the question.
Yes.
That's a good question. From what I know, about what we have done in the lab, when I put the flux meter in the outside of the room, just by the window, I reach only, I think the maximal is 10 micromolar photons, but it's not comparable because the distance between the sun and the flux meter is not the same that the one observed with the artificial light. So yeah, I think that we can expect having 10 micromolar photons, but we have seen during this study that it was sufficient for PHA production.
Yeah, maybe I have the wrong sources, or I'm not so well informed, but my understanding is that sunlight, typically if it's not cloudy, is a lot higher in intensity than artificial light often.
We'll have to change the flux meter. We will have to change the flux meters.
It would be good on a sunny day if we get any to put it outside and have a check.
Yeah. Without any clouds.
You could actually work with shading some parts rather than additionally illuminating.
Yeah, it could be.
Which of course in terms of cost may be interesting. Coming back to the whole thing of the illumination, so you nicely introduce in your abstract that photoheterotrophy is the way because it's bringing down production cost and the sun is an endless source of energy, and then the whole thesis is using artificial lighting. You do argument in your introduction in one of the chapters also that the cost of illumination versus aeration is off, let's say. So aeration is a lot cheaper. So I like to go a little bit in that direction. What about PHA production by purple bacteria in chemotrophic growth mode on fermentates?
So I remember about an article from Narincic that were using rhodospirillum room under chemotrophic conditions, and she obtained 20% of the dry weight as PHA. She
optimized for PHA production?
I can't remember. I think that she has used some nitrogen limitations, but I have to double check.
Anything known on PHV in chemotrophy?
I don't remember if she has observed PHV, but I guess that it is the same case in phototropic conditions. So it depends on the carbon source.
Yeah, but I guess if we are realistic, we consider the fermentates, right? So let's say acetate.
Yeah.
Maybe with a bit of valerate. Okay, so limited work on that. But given the economics that you sketch yourself, it's about 3 times cheaper to aerate versus illuminate. If I saw the cost expressed in dollar per kilo of COD in your introduction. Should that be the way to continue? Because
no, I think that the PHAs will always be more expensive than petroleum-based plastic as soon as we have petrols. However, I think that the idea of using phototropic condition is that there is a lot of co-products that can just bring down the cost of PHA productions. So I think that PHA will always be expensive, but we can just try to reduce this cost by having some nice co-products.
It's an interesting thought, because if it's of course balancing cost and benefits, but could you be a bit more specific on this co-product, because you sketched them also in the end of your presentation. You sketched loosely all the areas we could go into, but which one of these flows would you now choose And I know we can choose the most high value compounds, of course, always, but then we should not forget about the cost to get these compounds.
Yeah.
So which one of all these, you mentioned fertilizer, you mentioned fish production, etc. Could you elaborate a little bit?
I think that
You need to put your money on it?
actually we maybe will, but yeah, that's another subject. I think that the easiest one is to produce PHAs and biomass in the same times. I think that pigments are really interesting, but the costs that are necessary to extract and to purify the pigments and to separate the pigments are too much to consider this co-products.
Biomass and PHA, but then what is the use? You get the PHA out of the biomass, or you use the biomass containing PHA?
You can do both. I know that my choice is to produce PHAs and biomass. So to extract PHAs and to have the biomass, to recover the biomass.
And how does the biomass look if you've extracted PHA? Is it solubilized? What quality is there in left, and how are the precious compounds that you want to valorize in the biomass affected by such extraction?
Yeah, I think that you are talking about the contamination of the biomass using some solvents to extract PHAs. But I know that for the moment there are tons of techniques that are at the experimental scale that allow the extraction of PHAs without contaminating biomass. There is sodium acetate, there is supercritical carbon dioxide. We can use some mealworm. So I think that there is some idea that we can explore in these directions.
Okay. And what actually, I'm not per se after contamination, but how does the remainder of the biomass look like? What is in it that is still interesting? Are you mainly targeting the use of the proteins in there, or?
Yeah. I think, but I can't remember precisely, but I think that the purple bacteria and Rhodospirillum rubrum are good accumulator of phosphate, and so in that frame we can even if the biomass is without PHAs, the biomass is still interesting in terms of phosphate accumulators. So we can just use the Thèse biomass to feed some fish or some shrimps with it. And there are some carotenoids and
that phosphorus is a little bit low cost, low value. But phosphorus, I wonder if it also would stay. I understand. So the phosphorus could solubilize, or the polyphosphate could hydrolyze. Would it go to the solvent fraction, or would it be in a solid fraction?
Yeah, once again, it is in the case we are using solvents. I don't think that using solvents is...
Use something else.
Okay, use something else. Okay. I don't know. That's something that we have to study to see if the extracted biomass is still valorizable. But I guess so. There is, even if there is no phosphorus in the biomass, there is still carotenoids and some pigments. And we know that Rhodospirillum rubrum has some antioxidant properties. So I guess that it would be still good for the use.
So okay, good brainstorm. It will not be simple, but
yeah, nothing is simple.
And test a bit further there. The fermentation is an important pre-step to make the carbon source, let's say, affordable. Any clues on how to steer towards valeric acid? Because that's the one that you need to get a bit higher value PHA.
Yeah, there are some fermentation phenomena that are naturally enriched in. I don't think valerate, but at least propionic acid. I have a sketch in the manuscript the use of paper mills, fermentation, effluents or cheese whey that are rich in propionates, and that can just drive PHA production towards copolymers.
And is it because if it's just a choice of substrate, there's not too many paper mills or this type of things? Can you also play with the fermentation parameters, pH, temperature?
Yeah, that was the second part of the answer. Yeah, because I read some publications about. I mean, I think that you were one of the author, in which the pH was shown to modify and to modify the proportion of the different volatile fatty acids. So yes, we can definitely play on this. Just see what is the best pH. I think. Is it not pH 5 that you have demonstrated as main product condition for the production of valerate?
I should check again, but good answer. So this PHA, is it better than the other bioplastics and the other bioplastic production ways?
It depends which bioplastic you are talking about. If you are talking about PLA, I'm 100% pursued that it is better, because at least this polymers is biodegradable even in unmanaged environment, which is not the case for polylactic acid.
And if you compare it to cheaper types of biodegradable bioplastics?
If you are mentioning the one that we are doing with starch, I think that we are not going in the good directions, in the good way, because it means that we have to use some arable lands to produce PHAs or to produce bioplastics, and I don't think that using some food to produce bioplastics is the good way in which we have to go.
That's an interesting reasoning, but where is the carbon coming from in your paper mill?
Yeah, I get there is some stuff, but for the moment they are considered as waste.
Forestry, it's also land-based. Huh?
Yeah, but for the moment they are considered as waste, and we are not doing anything with it, so we can just try to valorize them.
I guess there are waste types of starch, like potato peels, or the label waste is of course something. Well, it's a co-product, product. But I agree, it's probably not the idea. It's like with biofuels, not a good idea to compete and try to produce a lot of things on the land and compete with food, because we need land for nature and biodiversity.
Yeah.
The key point on this PHA story, it's quite costly. Is that why the market is so limited, or is it the structural aspects of it, or the use?
I think maybe a bit of both. The market is not. I think it's not ready for PHAs, because there is no, at least with this process, because we don't have any large scale production of PHAs using this technique, so we can't approach the real cost of this bioprocess.
But PHA is on the market.
Yeah, but
it's being sold and produced, so there is a demand for it. Why is the demand not higher? Why is this market size so small?
Because petroleum-based plastics are too cheap. I think that this is one of the aspects that stop the PHA production and the PHA use in the market. Since the petroleum-based plastics will be at this price, there is no PHAs have no chances.
Okay, so mainly the price.
Yeah.
Okay. Sorry, I'm looking for the ones that are not taking. Okay. In the pre-defense, we talked about conversion economics of a carbon source to PHA. We did a small exercise. Acetate 500 euro per ton, 15% converted to PHA, it yields you already, just on the feedstock, 3,000 euro per ton PHA. And then you suggest succinate, which is an even more expensive.
Yeah.
So I wonder there if it's worth turning a very expensive feedstock into a less valuable product.
Yeah, I admit that the choice of succinate was not the good one. It was the one that were present in the thesis. So with the one that we know, it was to avoid the acclimation phenomenon that we have observed, so that we know that with this carbon source there is no, and at least the acclimation is restarted. And but we can explore some other carbon sources that are cheaper and that does not induce some acclimation.
Okay, good. Unlike my colleague, I'm a fan of open communities, but I mean, like my colleague Dan. And I was wondering, so you are aware of the common biorefinery route using open communities, and then sometimes leading to an enrichment of a, what is the name, plasticicumulans, acidivorans, or something like that, which is, well, even in real wastewater and pilot scale goes up to more than 70% PHA. So it seems like a cost-effective conversion. Again, the future, how do you see it? Should we not carefully benchmark and see whether this phototrophic production is the good one? Should we not go to the hemotrophic one and not per se with purple bacteria?
I think that both processes can be on the market. The phototrophic production allows the synthesis of interesting co-products that are not feasible using chemotrophic production. So maybe both can be used.
You mentioned the phosphorus. Phosphorus accumulating bacteria will happily thrive in such typical open communities with feast famine. That's their natural niche. So phosphorus levels, we could have.
I was talking about the pigments mainly.
Yes, true. But I thought you said that pigments.
Yeah, but if maybe that we can just have some phototrophic productions to produce pigments, and so that would present advantages compared to heterotrophic production, chemotrophic production.
It's good that you remain a believer in the phototrophic. Well, today at least you must. So, that's it's good to see. I think I will rest my case. Besides one final question, if you would have the freedom to continue on this, and funding is not an issue, which one of all the things now considered would be your interest? Would it be moving to more realistic conditions, higher TRL? Would you be zooming into specific things? If you can freewheel, what would you like to do?
Regarding the fundamental perspectives, I think that I will definitely go to the isoleucine biosynthesis pathway because it is something that is not explored anymore. I think that we have only 4 or 5 papers that are stating that this pathway could be an electron sinks. Then if I have enough fundings, I will go to the synergic effect that we observed in the presence of mix of VFAs, because this point can have both applications. It is quite interesting to study it for the fundamental point of view, but it is also interesting to study it for the scaling up of the process.
Well, I'd like to conclude with the fact that I wish you a good round of funding to pursue whatever you want to pursue. Thank you and congratulations again.
Thank you.
Thank you very much. Professor Hanson?
Yes, thank you very much, Guillaume, for this very clear presentation, for your works?
We cannot hear.
Oh, okay. I think.
Non, mais c'est sur YouTube de toute façon.
Not yet.
On va faire les cours. Tiens, ma soeur.
Voilà. Do you hear me? No? Completely?
No sound.
Ah oui, il est.
No sound because we don't have any. It is turned off. Okay, it is better. So thank you very Guillaume for this very pleasant present presentation of your works, of your 4 years PhD. It's a very long work with a very nice result, with clear explanation. You are quite, you do a very easy way to understand what you have done during this long time. I don't have a lot of questions, only one question, but I come back to my paper because we have already discussed about the life cycle assessment concerning biopolymer, and more precisely here concerning polyhydroxybutyrate. And when I look the literature, I see that unfortunately polyhydroxyalkanoates have less mechanical properties than other traditional polymers, and they are often used in blends with polylactic acid or with nanocomposite to try to obtain best properties for the use. So I think it's not so easy. It's right, it is a best biopolymer in terms of biodegradability, because we use already this for medical application. But what's your opinion concerning the conversion of conventional polymers or petrochemical polymer with this kind of polymer, if we have to use this in blend with other polymer, because it's more difficult to recycle or to biodegrade this one?
Okay, I think that there are two aspects of these questions. The first one is that the monomeric sequence inside the polymers is not fully understood for the moment, and there is plenty of applications that can be obtained just by varying the monomeric sequence. And for the second aspect of the question, I will definitely choose the incorporation of nanocomposite of cellulose, because it is known as biodegradable. So if we have to go in one way, I will choose this one. And I think that, yes, the physicochemical properties of this polymer will be enhanced compared to the natural polymers, but I will definitely not go to the polylactic acid incorporation.
Okay, in terms of recyclability, have you checked this one?
For the
nanoparticle of cellulose, I'm not sure it's easy to recycle.
The cellulose is the one that is used to produce the different, comment on dit ça? For the moment, the ISO stuff are using cellulose to test the biodegradability of one compound. So I guess that incorporating nanoparticle of cellulose will not change the biodegradability of.
It's not the term of biodegradability; it is the term of recycling. Because often, we recycle polymers, and when we look for the reuse of the polymer, not for the degradation of the elimination, but for the reuse, because if you reduce the need of resources, if it is bioresources, okay, but if we limit this need and we reuse already produced biopolymer, I think it's a real economy in terms of environmental or economical way.
Yeah, you're right. Yeah, I have to check if it is the same recycling way for it. I don't know, honestly. But is it the point is to recover the cellulose from the polymer, or
No,
just reuse it
We use all, if it is possible, we use all the polymer, the copolymer.
as it is?
About blends, it's copolymer, not real copolymer. It's a mixing of two sides of polymer, of two kinds of polymer, because often you need to produce a miscible blend, and you need to check the weight of your polymer because you need to have a good blend, a miscible blend. And often when we reuse, it is more mechanical reuse because it's a fission. So you heat your polymer and you create new pellets, and with these pellets you create new objects. So it's more mechanical. So it's during this mechanical treatment you may have some degradation due to thermic application, or so I don't know the stability against this kind of mechanical.
I don't know it too, to be honest. But I guess that we will have to adapt the different recycling plants that we already have to be suitable for these new polymers. I guess. I hope that we will adapt.
A last question: with your bacteria, what is the cell concentration you obtain in your medium after the grow stage? Because we speak always about optical density, but if we want to compare this result with some other result with other bacteria, it's often easy to have an information concerning the concentration in terms of gram per liter or number of cells per milliliter.
I have to double check with my colleague that is performing some bioreactor, but I think that we are at 0.6 gram per liter. I don't know if you can know, Spasa? Higher. Okay. So I will double check with her.
Okay. Thank you.
Thank you very much.
Very nice work. Very.
Thank you.
Happy to be in your jury and to learn new things. Thank you very much. Guy.
Thank you.
Thank you very much.
Thank you.
Is it here? Okay. Yeah, but first I will ask if the supervisors have any question. No. So usually in PhD juries and PhD defense, there is also the possibility that the public has some question. It was still possible virtually, but I think we have no question this time, so you are lucky.
Yes.
So now it's my turn to congratulate you for your very nice work. I really enjoyed. I really enjoyed reading your thesis, because I'm not at all a specialist in this field of microbiology, and especially the bacterial metabolism, which seems so complex to me. That was really interesting, really clear, and also congratulations for your presentation, which was also very nice.
Thank you.
I've just a couple of questions.
Questions, sure.
I was, as a totally non-expert in the field, I was really surprised about you use kind of a family of related molecules, the volatile fatty acids, which to me seems really close one to another. And with those molecules, you have a lot of different metabolism, which I would have expected if you use amino acids or sugar.
In fact, the metabolic pathways are not so different. We have kind of in the central carbon metabolism, we have different pathways, but when we are using acetate, so we have the use of ethyl-manonyl-CoA pathways, which is in fact the one that is also used for butyrate when it is divided into converted into crotonil-CoA, and we have the same effect with propionate and valerate. So we have a lot of common metabolic pathways that are used to assimilate those VFAs. What is interesting is to find that using those different volatile fatty acids, we can have different pHs, just because one pathway is more expressed than in one condition than in another one.
Okay. And it appears to me that the number of carbon seems to be important to know in which pathway the molecule will go on. Do you have any idea what would be the result if you would use longer fatty acids?
We have some ideas because one colleague is using hexanoates, and we have seen that the acetylmalonyl-CoAs pathway was also used, as well as the isoleucine biosynthesis and degradation pathways. If we are considering longer fatty acids, then I think that we will drive to the beta oxidation process, and so we will definitely release acetates as products, and so ultimately we will be facing some assimilation through the acetylmalonyl-CoA pathway once again.
Okay, thank you.
Thank you.
And regarding the application side now, which is also an interesting part of your work because it's a more fundamental work, but with clear application. So your aim was to try to increase the amount of PHA you can produce, but in view of this kind of equilibrium between different pathways, and if you change a little bit something on one side, everything change on the other side. Do you think it's realistic to have more than this 15% mass PHA? Or it's just in some specific laboratory conditions that you can reach more?
I think that it is feasible to obtain more. Here we are only considering the stresses that we can apply to the cell, but we can, for example, imagine that we can limiting the phosphorus or sulfur concentrations to once again increase, and in this case using the feast and famine processes plus the light stress concepts that we have demonstrated here.
Okay, thank you.
Thank you.
And one last question.
Yeah.
Of course, I had to ask a question about electron microscopy.
It was not my part.
No, I know, but no, it's just out of curiosity. I noticed that the PHA granules, when you observe them in TEM, there are always like two phases in them: one electron lucent and one more electron dense. Do you have any idea what are those two phases? Are they related to some processes or just an artifact of preparation?
I don't know. The electron microscopy was performed by another PhD student, so I have to check with him. I hope that it is 100% PHAs, but yeah, maybe it will be interesting to study it deeper. I don't know what can it be.
Okay, I don't know either. Okay, thank you very much and congratulations once again. So if we have no more questions, maybe we will deliberate. Yeah. And I don't know if we're staying here or... Okay, so now we will have a short deliberation, and maybe you can...
For the guys on YouTube, I will just switch off the microphone, and then when the duration is over, then I will go back. We will go back. Thank you.
compliqué. On va avoir des masques. On va essayer. Okay, thank you very much. So now you have reached the last step of this long process. So I have to switch to French because I have to read what is written on this diploma, which is mandatory. Donc voilà, vu le décret du 7 novembre 2013 définissant le paysage de l'enseignement supérieur et l'organisation académique des études, nous, présidents, secrétaires et membres du jury chargés de conférer le grade académique concerné, déclarons que Guillaume Bayon-Vicente, né à La Louvière le 1er octobre 1993, a obtenu en l'année académique 2020-2021 le grade académique de docteur en sciences. So, congratulations. Now you also have to sign your diploma.
You have a pencil, a black pencil.
Right there.
Black or blue, not red.
So, yeah, this one here.
Yeah, no, absolutely.
Okay, so congratulations once again. We cannot shake hands, but and I don't know if your supervisor want to
I
say.
have some two or three words. First, I would like to thank the different members of the jury. Thank a lot Siegfried, Robin, Daniel, Annelies, and Patrick. It's very important for a candidate to have a good jury. And I very appreciate your interaction with the candidate during the both defenses. But it's terrific for us. It's not possible to drink a beer together to celebrate this thesis. But officially, I will send you an invitation to come in Mons to visit the laboratory just after the COVID. Thank you very much again. So Guillaume, it's your day. Officially. That's right.
Can I say one word?
Yeah, please.
I just want to say to Guillaume, it's a very nice thesis, and I really enjoyed it very much, and I enjoyed the interaction and the presentation, and I wish you well in the future.
Okay, thank you
It was also a great pleasure to be invited, and I'd like to thank the thesis supervisors as well for this honor to be present, even in these difficult times. It was enjoyable.
Yeah.
Thank you.
Thank you very much. So Guillaume, it's your day. Officially, you have my colleagues, a doctor. A thesis is a long story, 4 years ago. And during this time, and during a thesis, you have two different aspects, the scientific aspects and the human aspect. And I very appreciate your evolution of the different aspects during this time. And congratulations for your thesis. And of course, Baptiste, thanks to support this guy during 4 years and for your supervision of this thesis. Really, this domain is now your domain for the lab. Thank you, and good luck for the future. Thank you very much.
C'est mon tour.
Il a pris un...
Ah bah ouais, j'avais quand même préparé un petit truc. So first I would like to thank the jury for their constructive comments during the private defense and the public defense, and the time they have spent reading this thesis. Your commentary definitely strengthened this manuscript, and I would like to say that I couldn't dream about a better jury, since you are all expert in what you are doing. So once again, thank you very much. And now I will switch in French for the rest, because I have to thank some people. But thank you very much. Thanks again. Bon, belle année 2020. Hein. Elle se termine pas trop mal, je pense. Donc, premièrement, je voulais aussi remercier les membres francophones de ce jury, on va dire. Merci pour vos commentaires, vos questions. Ça a vraiment été un plaisir d'interagir avec vous durant ces deux thèses. Je voudrais remercier mes deux promoteurs, donc Rudy Wattier et Baptiste Leroy. Donc, professeur Rudy Wattier, merci à vous pour les opportunités que j'ai eues. Toutes ces soirées à parler longuement qui m'ont fait rentrer très tard chez moi, et pour les bons contacts au bon moment. Donc merci à vous, ça m'a fait plaisir d'interagir avec vous et de voir cette thèse de temps en temps sous un autre angle. Merci à toi Baptiste pour ta disponibilité, tes réponses à de nombreuses interrogations, des nombreuses questions qu'il y a eu tout au long de cette thèse. Ça a vraiment été un plaisir de travailler avec toi et de dormir avec toi de temps en temps aussi. Mais bon, ça on le garde pour nous. Donc merci à toi et j'espère que je resterai ton héros préféré pour l'éternité. Je voudrais dire quand même que travailler en trio, c'est pas toujours très facile. Il y a de temps en temps des petites brise-brouilles, il y a des changements d'avis, des divergences d'avis, mais j'aimerais dire que c'était aussi une belle aventure pour moi et que vous êtes tous les deux pas si différents, vous essayez de transmettre votre passion comme vous pouvez et vous avez réussi. Donc merci à vous et ne changez rien, ou presque. Ouais. Donc merci aussi à l'équipe de Materia Nova, je ne sais pas s'ils sont sur YouTube en ce moment, mais ils ont réussi à apporter le support technique que j'avais besoin pour cette thèse, donc merci à eux. Je ne vais pas tous les citer parce que je vais en oublier et ça va en vexer quelques-uns, mais merci à eux. Merci à mes collègues qui sont restés au labo aujourd'hui, mais cette thèse n'est pas la même sans vous, donc merci à vous tous. Un peu cliché, mais merci à la famille, merci à la famille qui est sur YouTube, merci à mon père, ma mère, ma soeur, qui ont fourni un cadre familial assez unique pour cette thèse. J'avais presque oublié Médéric, qui m'a suivi pendant 9 ans, et qui aujourd'hui fait l'ingé son, donc si tout ça est possible, c'est grâce à lui. Et finalement, j'aimerais remercier Camille, qui est avec moi depuis 12 ans, qui me supporte, et qui a supporté les samedis et les dimanches à l'UNIF pour que j'ai ces résultats-ci. Donc merci à tous et à la prochaine. Bye, thank you very much.
Thank you, and we will remember the voucher for the beer.
Yeah, sure. Bye-bye, thank you very much.
Bye.
Congratulations.
Thank you very much.
See you later.
Bye-bye, everyone.